second afternoon session. We have now Paola Arrubarrena, is that right? With anomaly detection and radio astronomy data.
Thank you.
Please go ahead.
So, hi everyone, good afternoon. Thanks a lot for being here, and thanks a lot for the organizers for the invitation. I'm very glad to be here today presenting our work on anomaly detection and radio astronomy data. And of course, this is joint work with some of the people that you already know, with Maud Lemercier, who is a postdoc at Oxford, Bojani College, who was our astronomy contact and is based here actually in Cambridge, Tom Cass, professor at Imperial College, and Terry, which you already know, and he gave a very nice talk at the beginning, introducing some of the stuff I'm going to be talking about. So, okay. I'm going to start my talk with a short introduction on astronomy and radio astronomy, and why this is a interesting topic and has a very specific issue we want to tackle. So astronomy is the study of the universe, and how people have been doing this from the very, very beginning is from studying the light of any interesting source out there. And you know that light is a very weird thing, but one of them is its wave. So it has its electromagnetic spectrum decomposition. So if we look at very high, very high energy wavelengths and very short ones, we could have, for example, gamma rays. If we go through the spectrum, we're going to get the visible light that goes through around 400 to 700 nanometers, and that's what our eye can actually see in the form of colors. And if we keep stretching the wavelength, we're going to reach into radio waves, which are the ones that I want to focus today, and they're going to be quite long and low energetic, from centimeters up to kilometers long. And it's important to study every part of the spectrum because it's going to tell us a different part of the story. For example, in this very nice picture of the Andromeda galaxy, which is the closest galaxy to our Milky Way, it's also a spiral galaxy. When astronomers study different parts of the spectrum on it, sorry about that. X-ray, that's the first one. Yeah, if they look at X-rays, well, maybe the picture is not that great on the projector, but they can see more study more the supermassive black hole that it's supposed to be in the center of this galaxy. Then if they move to ultraviolet, they can see more about the structure and where new stars are forming or so. Then they move to visible light, and they can see all of the millions of stars there, but you can also see some of the dust, so maybe some objects are behind this dust. So if they want some clearer image, they will go to infrared, where you can see clearer the disk and the centers as well. And at the very end, these radio waves, which are going to be more sensitive to hydrogen clouds and hydrogen emissions, which I'm going to be mentioning later as well. So, okay, I'm going to be mentioning these main radio observatory, radio astronomy observatories, because I'm going to be showing some data taken from here. The first one is Hera, which is located in South Africa. It's composed by 350 antennas, each one of 14-meter diameter, so they're quite big. And it has this hexagonal structure. The second one is the MWA array, located in Australia, composed by 128 tiles, which are these tiles. They're really an array of smaller antennas, 4x4, spider antennas I call it. And I'm going to explain later more or less how this works. And the third one, and I think Terry also mentioned it in the morning, is the SKA, or the Square Kilometer Array, which is under construction. So I'm not going to show data from here because we still don't have it. But it's supposed to be the largest and most powerful radio observatory ever created. And it's going to use antennas from Hera and MWA and several other observatories. So you can question yourself, or why is people spending so much time and money still in radio astronomy building larger and more powerful observatories? And besides... Sorry?
Did they get a job?
Yeah, they get a job, definitely. There's hundreds of people working on this. also, besides getting a better map of the universe, they are quite interested in finding the epoch of our ionization signal. And what it is? Well, we have here a timeline of our universe. It's theorized that the Big Bang happened something like 13.8 billion years ago, which is this theory that explains the creation and expansion of the universe, starting from an initial state of very high density and temperature. And at some point where the universe expanded and cooled down enough, we reached something that is called the cosmic dark ages, where we really don't know what was happening there. It lasted quite long time, something like 500 million years, up to something, we don't know still what, ionized the neutral medium, the neutral background, and created a sort of imbalance that led to the creation of the stars and the galaxies. So our galaxy was created more or less around here, 1 billion years after the Big Bang is theorized. The only thing that we know from the cosmic dark ages is that we had all of the hydrogen ever created just sitting there. And hydrogen, it's a pretty stable configuration. It's composed by one proton and one electron. And most of the times, both of their spins are aligned. So the spins is this intrinsic property of particles, sort of an angular momentum, but it has direction. And what can happen once in a while, very rarely, but it happens, is that the electron spin can flip on direction from up to down, and in doing it so, or down to up, and in doing it so, it will emit a radio wave, very characteristic radio wave, the so-called 21 centimeter line of hydrogen, or emitted in 1420 megahertz. This is a very well-known phenomena. I'm going to show an example of that in my next slide. But astronomers know that this happened. So that's why they think if we had only, if we had only hydrogen sitting there for millions and millions of years, well, this kind of effect should have happened also back then. Now, they're looking for this signal. They're not looking for it in a 21 centimeter line because, of course, the universe has expanded and stretched everything on its way. So they're going to be looking at around 120, 180 centimeters, or they're building the telescopes to look at 50 to 250 megahertz. The important part and the exciting part of finding this type of experimental evidence of what was happening here, it can shed light of what caused this sort of imbalance that led to the formation of first stars, as I mentioned, but also give information on how long it lasted, what were the conditions back then, and so forth. So it will help building the puzzle of the early ages of the universe. And mention a little bit more about the hydrogen, 21 centimeter line of the hydrogen, of the hydrogen atom. Here's an example of its emission when astronomers look at the center of our galaxy, the Milky Way. So it's a spiral galaxy, and if you know our solar system, it's at the very outer part of it. But if they look at the center of it, they can see this 21 centimeter line jump, or 120 frequency. And this kind of things, as it happens very once in a while, it's observed in very old objects in the universe. For example, our galaxy, or the Andromeda galaxy that I showed you before, or so on and so forth. These other two peaks comes from hydrogen clouds, and because of the reference they were taking for this picture. But just to mention, this is a very well-known phenomena that we know it happens. Okay. So far, so good. So how do astronomers actually get their signals, or read the signals, these kind of radio signals from the universe? If you remember the pictures I showed you earlier, there were not only one antenna. They were an array of antennas. And the reason is because if you would have only one antenna, the resolution is a function of the wavelength and the diameter of your device. And radio waves, as you remember, they're the longest wavelength, so they're going to have a very long wavelength. So in order to have a good resolution, you will need to build huge antennae, and that's not very handy. So what astronomers do is that they take into advantage a so-called interferometry, where they're gonna superimpose the output of two antennas by multiplying their voltages and integrating over time. So this is called the correlator. We're gonna correlate the output of two antennas, get this fringe pattern, and we know that a correlation function has a spectral decomposition given by its power spectrum. So that's exactly how our data is gonna look like. For each antenna pair, we're gonna have an array of complex numbers ordered in time for each frequency channel. So far, so good. But of course, there's a huge problem. And I don't know if someone thought about radio broadcast or TV broadcast when I was talking about radio waves. And the reason is that there's a lot of noise coming from human sources that can reach to the radio observatories, antennas or observatories. And it can be really anything. Like, these observatories are built in very quiet areas, but still there are a lot of things people cannot control. It can be created by power lines, radio and TV broadcasts, as I mentioned. Even if someone turns on their car close enough, this can cause noise. And yeah, so I'm gonna be calling the noise its radio frequency interference, or RFI. And in a paper from the MWRA in Australia, they actually tell the story on how they were getting some noise, some RFI. And then they saw that it was coming from, apparently a plane flew in a certain region with a certain angle, and it reflected TV broadcast from some very far away town. So there's a lot of things they cannot control. There are even projects thinking on building some observatories in the moon, but I don't know, they will still have some RFI up there. So as you can imagine, it's going to be very important to detect even the faintest trace of RFI, because these can give information to astronomers on how to mitigate it, because maybe they can learn where it's coming from and try just to quiet it. And this is an example of RFI. In this paper, the authors were introducing AO Flagger, that it's a framework that tries to find this RFI. But in these plots, you can see where we have time and frequency. All of these lines is actually noise. And it looks pretty ugly. Imagine you're looking for your signal to be somewhere around here. Well, this really doesn't help anything. And Bojan was telling us that sometimes in Hera, they had to throw away months and months of data because they were getting horrible RFI. And this is a lot of money and effort that it's just thrown away to the trash. So, of course, this is a pressing issue, an important one. And that's exactly what we were trying to do. So we built a framework called SIGNOVA, Signature Novelty Detection, that is trying to find RFI as an outlier. So yeah, how does SIGNOVA works? Well, remember that I say we had our array of antennas. If I want to focus in antenna I, this is exactly what I was mentioning. We're gonna have the output of all of the antennas, of all of the data of the antennas connected to antenna I, because everything goes per antenna pairs. So we're gonna have our stream of complex numbers ordered in time for each frequency. The first thing that we're gonna do is that we're gonna apply the signature to each one of these. And we define the signature, and you listened to it already in the morning. For a signal x in from 0 to t in RD, we're going to denote the signature as this set of iterated integrals, but we're going to truncate them at a certain level. And this, we use it in order to vectorize our sequences of observation. So now we're going to get vectors with characterizing our signal, which is very useful because then we want to build feature vectors with it. So how we're going to build a feature vector for antenna I, we're going to average over all of the outputs and the signatures connected to this antenna. And we're going to do this for all of the 200, 300 antennas that we have in our data set. Okay, So that's the first key component. The second one is that we're going to build a data-driven anomaly score. And the first thing that you need to know is that assume that I have access to clean data. And I will have access to clean data because even if I don't have real clean data, a good simulation works, and I'm going to show you results about this. So imagine I have access to to clean data. And I'm going to use it to learn from it to build this corpus of normality that you'll also heard of it in the morning. And yeah, exactly. From clean data, I mean RFI free. And with this corpus of clean data, I can calculate the sample mean, the sample covariance matrix to apply the Mahalanobis distance. So this is the definition of the Mahalanobis distance. It's going to use the inverse of the covariance matrix that I'm going to build with my clean data set, with my corpus of clean data. And it's going to calculate the distance between an input and an element xi of my corpus of clean data. So this is nice because it's going to standardize it, decorrelate the data before calculating the Euclidean distance. And it's going to be a unitless approach. So then with this, I'm going to have this collection of distances, and I'm going to get the nearest neighbor, or the minimum of them, to build my score. And we're going to do this twice. First, to get calibration scores. So I'm going to calculate this minimum Mahalanobis distance between my corpus of normal clean data and another set of clean data. And I'm going to do it again with the same corpus of clean data, but the minimum Mahalanobis distance with my test data set. So like this, I'm going to have two sets of calibration and test scores. And the third step is that, well, now that we have our scores, our scorings functions, we want to localize where in time this RFI happened in order to build plots similar to the ones that I showed you before, where I showed the contamination of the RFI. So this is what we want to give to astronomers in order to compare apples to apples. And how we're going to localize it? Well, we're going to use a segmentation algorithm that it's going to work like this. So for the test data, we're not going to apply the signature to the full interval of time. We're going to just apply it to a small interval of time. And what's going to be defining these intervals is going to be this algorithm called pi segments, which was developed by Sam Morley from the Alan Turing and DataSig and Terry. What pi segments is going to do is the following. Pi segment is going to look at one frequency channel, the full segment, like this. So imagine that in this segment I have RFI in this part and RFI in this part. So what it's going to do is that it's going to start dyadically partitioning. So it's going to start partitioning, and it's going to ask the question, is this interval clean? And well, obviously it's going to get a no, and in this part, no. The way this asking if an interval is clean or not is by a thresholding function that I'm going to show in the next slide. But then it's going to partition again. Is this interval clean? No, no. Here it's going to get a yes. So where it finds the clean interval, it's going to start expanding it to the left and to the right, up to it finds all of the clean, the full clean interval. And by doing this, we're going to keep on finding the longest and the longest clean intervals. And by consequences, we're going to reach RFI. So we keep this information, especially for plotting. So the decision threshold on how pi segment is going to ask if the interval is clean or not works like this. Remember that I told you that we're going to have two sets of scores. We're going to have our calibration scores and our test scores. Our calibration scores are the clean scores. So we're going to take those. Here's an example. As they're clean, I would expect them to have a peak around 0, which is shown here, and it's nice. We're going to fit a curve to our clean scores. And then we can choose a confidence interval high enough, meaning that maybe I can threshold it knowing that 99.95% of all of my clean data is below this threshold. And then I'm going to compare it to test scores. So for one frequency channels, I compare it to the scores in green, calculate the median of them, and if this median is below my very high thresholding function, I'm going to assume that this interval is clean, or PySegment is going to know that this interval is clean. This is how it looks if I compare it to a contaminated test scores. It's pretty difficult to plot because they're orders of magnitude higher than my threshold. But of course, this is a very obviously contaminated interval. So that's how we're gonna find everything. So okay, this brings me already to show you some results. The first results that I'm gonna show, and you already saw in the morning, are from real data taken from the MWA array in Australia. We chose this because SINS, which is another astronomical framework, on this paper, they reported that they saw RFI in 2 frequency channels. So again, these plots are going to have time and frequency, and they reported only this data set to have contamination in these 2 frequency channels. So what we did, as this is public data, we downloaded 9 consecutive data sets, 5 before and 3 after of what was reported in this paper. We run the data sets in their following frameworks, and then we concatenated the results. We also checked on AO Flagger because it's another widely used framework by astronomers to try to find this RFI. And well, we could see that these 2 frequency channels appear, maybe in AO Flagger a little bit less here, but okay. We run it again with Signova, and these results were very nice to see because first we could see the same RFI they were reporting. So this was reassuring. The second thing that we saw is that, as Bojan pointed out, is that we could see continuity in the RFI, and that's what we would expect. And the other thing, I'm not sure if you can see, but we see RFI in these 2 data sets that we correspond to these 2, where the other frameworks, they cannot see it. And it's exactly in one of the contaminated frequency channels, which tells me that maybe the RFI was already there and it was too faint for them to detect. But these 2 data sets with RFI will correspond to about 5 minutes of observations. So if you want to do online analysis, this will matter, of course. The second results that I'm going to show is with simulated data because we wanted to know how much noise we were putting on the data. Again, we have time and frequency, and this plot is only showing the amplitude to just show how much noise we put in here. But we very high contaminated the top and the bottom frequency channels, constant in time. But by very high, I mean it was like 30 times the baseline noise. This one was very low contaminated, also constant in time. And in this plot line, we varied the contamination across time, starting by very low and making it higher. With SINS and AO Flagger, it seems they don't have any problem seeing the RFI that varies over time. But even if the RFI is very high, they seem to have a problem seeing constant RFI. And it's a way how they work. For example, SINS applies some kind of average over their antenna. So they might lose this type of information. And well, nicely we saw that we were able to see all of the types of RFI. And lastly, this is my personal favorite example because it's going to combine real data and simulated data. So what happened here is that Pascal Bojan's PhD student, they both work at Hera, and he was analyzing some data. So this was Pascal's plot. So sorry about the axis. They're like the other way around. We have frequency and time. But the way their Hera team were analyzing the sky was by fields. So they were dividing the sky in different fields, field A, B, C, and D. But as the RFI is here on Earth and it was arriving to the antennas, you can see they were seeing some RFI in this region across all of the sky. There's one frequency channel that it seems to be contaminated, this one, I hope you can see it. But Pascal was having trouble seeing it in field C, the one that he was processing. And yeah, so they were nice enough to lend us their data, but they only had this piece of data, which was real data. They did not have any clean data that they could provide us. So there are several simulators out there that can make a pretty good simulation of the Hera array with different types of noise and so. And we actually do that. We did that. We used the Hera simulator to simulate all of our data, clean data used for our corpus and the calibration scores. And then we applied it to this test data. And it was very, very nice to see that for this field C, we could see the RFI that it's appearing at the beginning, but also around 160 megahertz, we saw this RFI that was a bit difficult to see. So yeah, this was actually a very nice example combining simulations and real data. Well, I still have a lot of time, so just very quickly a couple of minutes just to give continuity on Terry's talk. I was part of a CDT Summers project, so this has nothing to do with astronomy, but I was supervising for CDT students from Imperial College for a summer project, which are very nice but short. And luckily we got MEG data, so data taken from brain activity, magnetos, I cannot pronounce this, but it's mainly magnetic data from brain activity. The way they do it is that these magnetic fields are perpendicular to the electric fields produced by the neurons. And they put something around 300 sensors in the head of the patients, and they just get all of their brain activity. This is how the output looks. So for each sensor, we get sort of a spectrogram. What was also very nice is that this type of data was also in the form of complex numbers, like array in time. So it could be translated somehow to the astronomy problem where we have antennas here. So yeah, we have this data from 53 patients. But the way this project worked is that we throw sort of a challenge to the students, where the neuroscientists that gave us this data gave us all healthy patients, but not one. One was an unhealthy patient, but we did not know which one. And the goal was to find which patient was the unhealthy one. Now, as we needed to build this corpus of normality and have our calibration scores, he told us 20 patients that were healthy, but the rest we had no idea. So with these 20 patients, we were able to build corpus of normality, calibration scores, and then test it on the rest and see if we could see. We only compare scores. So, okay, we could find the unhealthy person. It was person 11. This was nice to see. And we did it by comparing the scores distribution. So for healthy persons, the scores were very small, like 10 to the minus 5, 10 to the minus something. And when we reached or seeing the scores of person 11, they were really off. They were very far away from our corpus 8 to 11 or so. So yeah, this was just some short project that we had, and it was nice to see that it worked. So yes, this brings me already to my conclusion. Our astronomy paper is already on the archive with the same name of the talk, so novelty detection and radio astronomy data using signatures. We have our code there, so please check it out. And well, I presented where we use these novelties with signatures as vectorization. We learn what normality is, and we use pi segments to segment and find these RFI. So thanks a lot for your attention.
So we certainly have time for questions. Start.
So in the last example, so if they didn't tell you which the 20 equations, what would you do? I mean, you don't have a corpus of normality for sure. Can you try out or some clustering?
Yeah, probably some clustering or so, but this methodology really relies on learning what clean is. So I think, yeah, that will be some problem for something else, maybe. Yeah.
I have a related question. So how many, is there a number that you can give? How many do I need for this kind of base truth data? That, you know, so why 20? Could it be 10? Could it be 3?
Yes, no, it was, yeah, it was not a number that we choose. It has to be representative. So, I mean, you cannot have only 1 or 2, because I think that will not give you the enough numbers. So yeah, maybe there's a limit on how low we can go on clean data. But yeah, I guess by testing we can know. But yeah, I will not take one patient only as a clean one.
And was an obvious thing after you looked at the data again? Can you then see obviously that this trace of the patient then was different anyway, or would you have found it without it? That's my question.
So okay, so funny thing is that another group also got the same data, so we were kind of competing with them, and they did some other type of process, and at the beginning they could not find it. I don't remember what they used, but I mean, I'm sure there are other methods to find it, but it was nice to see that this worked.
And can you give an idea how long it takes actually? So because you have 50 traces, yes? So how fast is it? Does it take 10 seconds? Is the whole system, how long do I need to compare these kind of 51 traces or so from these patients?
So how long does it take to run? I don't have the numbers in my head at the moment. But
sorry, just an indication. Is it hours or days?
No, a couple of minutes.
Okay.
Yeah, these were not big data sets as well.
So the scales of the data set and probably the number of traces, isn't it?
A question about the transition at 21 centimeter.
How
do you distinguish from very old events from the beginning of the universe and new events that occur now?
Yeah, that's a good question. So for looking from this epoch of ionization signal or so, they are based on the so-called redshift. Mm-hmm. So they know how much the light should have a stretch in so many years. Oh, I see. So they're looking for a certain stretch in light.
It should be longer wavelengths.
Exactly.
Okay.
Exactly. Yep.
And obviously the frequencies you said 1 gig over 1.2 gig, and then you look at interference at 100 and something megahertz. Also, you sort of said compare measurement from another antenna which was in Australia. That could have a different sensitivity receiver, however. Therefore, how do you compare one antenna against another one?
So my understanding is that the observatories are built to look in a certain range of frequencies only. So do you mean the SKA that wants to combine?
I mean, every antenna has got sensitivity which might be different from another one. Therefore, you get different signal to noise.
Yeah, but I'm sure they can correct for. Yeah. They're pretty big arrays, so yeah.
Are there any other questions? Oh, the same Paola again.